All right, well, good Monday morning. Welcome to, what are we on, week 4, I believe, of the quarter already. It's flying by. But today our plan, we're going to go ahead and talk a little bit more about the forms of integration that lead to inverse trig substitution. Specifically, I want to show you completing the square. I want to remind you about how we do that. And then we're going to start doing applications. We're going to start seeing what else can we use integrals for, because right now you've seen it as the way of finding signed area. And while that is useful, there are lots of other things we can do with them. And so we will talk a little bit about another application. It's another area application, but that's where we're going to be going for the next few weeks. All right, but before I do that, I just wanted to open it up to you guys, see if there are any questions about the homework or anything else that we've talked about. And speaking of the homework, let me just make sure I tell you guys all this. I extended 1.7, the section on inverse trig, to Wednesday night at midnight, just because since I haven't had a chance to talk to you about completing the square, I didn't want to leave you guys hanging there. So just be aware, 1.7 is now due Wednesday night at midnight. But anyway, are there any questions about the homework? Anything we'd like to talk about? All right, so Chase has a few from 1.7. Thank you. So 7, 8, and 11. Any others? All right, so I'm not hearing or seeing anything else. So, oh yeah, so Devin number 7 from 1.7. All right, I got that on the list. We'll make sure that we do that as well. All right, cool. Well then, let me go ahead and share my screen and we'll go take a look at those. All right. So we got 7, 8, and 11. Let's go take a look at 7 first. All right, so this one just says compute the given improper integral. Says enter the exact value of the answer. Okay, so I know it just says improper integral. We haven't talked about improper integrals, and it's not supremely relevant to this right now. But what it means is that one of the endpoints has an issue with it. Like if you look at this function, notice the endpoints of this integral, 4 and 5. 4 is a bit of a problem because if you plug in 4, you get division by 0. Right? So we can't exactly plug in 4 into this function, but it is possible that we can plug 4 into the antiderivative, and therefore when we're doing the fundamental theorem, we can still evaluate it. So that's the only thing that improper means. So if you saw that and then went, wait, I don't know what to do, that part just means that there's an issue with one of the bounds. But let's see if we can just do this. Let's see if we can find the antiderivative of 1 over the square root of x squared minus 16, and then go from there. All right, so I'm going to go ahead and switch to a whiteboard. And we'll see what we can do here. All right, so the function that we're integrating, well, it was the integral from 4 to 5 of 1 over the square root of x squared minus 16. All right, so what do you guys want to do? How are we going to attack this? Ideas, thoughts, suggestions? other than let's just ask Bruce because he knows the answer and he'll tell us. All right, so
can we get rid of the square root?
Okay, so we got a couple things. So I've got the, can we get rid of the square root? And then, okay, I think Alexis just corrected herself. She said, let's let u equal x squared minus 16. At first she said u equals x. And I was going to say, let's never let u equal x. That's always a bad substitution, but we'll address the x squared minus 16. But Mariola, your question, can we just get rid of the square root? Unfortunately, no. We can't just get rid of the square root, even though x squared and 16 are squares. We can't just eliminate that square root because they're being subtracted. If they're being added or subtracted here, you can't just get rid of the square root. So if this had been the square root of x squared times 16, then yeah, that would have just been x times 4. Could have gotten rid of the square root. But the fact that it's a minus means that we can't just eliminate it. So I know we want to, but we can't. If that was a perfect square trinomial, what I mean by that is if it said, like, let's just say x minus 4 squared in the square root, then yes, we can get rid of that. But unfortunately, x squared minus 16 isn't a perfect square, right? Because x squared minus 16 is x minus 4 times x plus 4. So there isn't anything we can do algebraically to simplify that or reduce that. So we're just kind of stuck with the form as it is. Okay, so let's think about Alexis's suggestion of letting u equal x squared minus 16. That's never a bad idea because u substitution, if we got that square root stuff, square root of u is much easier to use and is definitely better. Okay, so let's try that. So I'm going to go ahead and write over here u equals square root of x squared, or no, not the square root, just x squared minus 16. So let's see what everything turns into. So du is going to be 2x dx. So when I solve for dx, I got du over 2x. So let's put all this stuff in. So the dx is now a du over 2x. The 1 over square root of x squared minus 16 is 1 over the square root of u. But we still have that x. Crap. We still got an x. That's a bit of a problem, right? But we can solve this thing for x to change that back into u. So I've got x squared is equal to u plus 16. So x is equal to the square root of u plus 16. So let's put that in there and see what that does for us. So we have 1 over the square root of u, du over 2 square roots of u plus 16. And actually, while I'm here, let me go ahead and change my bounds. So when x is equal to 4, u is equal to 0, right? 4 squared minus 16 is 0. And when x is equal to 5, u is equal to 9. So there is that integral, all in terms of u. Let's just make it a little bit prettier here. We'll put a 1/2 out front, going from 0 to 9. And I'm actually going to combine those square roots by multiplying them together. So I get the square root of u squared plus 16u. All right, so if we do that substitution, we went from this black one to this red one. I don't know if that's any better. right? Like this one, if we go back and look at it, it's not the right form for any of the inverse trig. If it had been 16 minus x squared, if those had been flipped, it would have been perfectly ready for inverse sine. Well, okay, but it's not inverse sine. So we can't do that. This one also doesn't look like any of the forms. So at this point, you might be thinking, all right, well, we're sunk. But we're actually not if we complete the square. All right, so we should probably talk a little bit about completing the square and all that good stuff. But before I get to completing the square, are you guys okay with the steps to this point? We're all good? All right. Okay, so here's the trick. Here's what you want to do. We're going to want to complete the square. So actually what I'm going to do, I'm going to pause this one for a second. Let's go look at the others because I want to show you a couple of more straightforward examples of completing the square before we come back to completing the square. All right, so I'm going to do that real quick, but okay, so Alexi says you have to use a natural log formula. You don't have to, but that will work. I'll come back to that. And then, but real quick, so Ayers explains, can I explain how I got the new interval from 0 to 9? Sure, let me just show you that real quick before I leave this guy. So if you take these bounds 4 and 5, you can plug them in here for x, since they're x values, and that will give you the corresponding u values for those x's. So for example, when x is 5, you get 5 squared minus 16, which is 9. And then the other one, you get 4 squared minus 16 equals 0. All right, cool, you see? Awesome. Okay, so we'll come back to this one. Let's just pause this for a second because it's gotten us to a form that we haven't talked about yet. So let me just hold off on that for a second and then we'll come back to it. So instead, let me go ahead and jump to the next one that was asked for, which was number 8 from that list. So we'll jump back to the exercises list and take a look at 8. Okay, cool. All right, so this one, same kind of story, right? We're looking at that and going, well, that's not exactly a form we know how to do. So we need to see if there's a way to change it into a form that's good for us. All right, so let me go ahead and go back to the whiteboard. We'll write this one down and see what we get. So let me clear this set. And somebody's mic is picking up their papers and stuff moving around. If you could mute yourself, that would be awesome. Thanks. Click the wrong button. All right, here we go. So we have x to the 5th over the square root of 1 minus x to the 12th dx. All right, so let's think about you doing some sort of U substitution, right? This is begging for U substitution. So here is a choice for you, kind of like what we just did on the last one, is what if we let u equal 1 minus x to the 12th? So we just get the square root of u on the bottom. That's pretty nice. Well, du then is going to be minus 12x to the 11th. And it's at about this point that I start not liking this. Do you see why I'm not going to really like this one very much? Think about what's going to happen. When I solve for my dx, I'm going to get an x to the 11th, which is going to leave me an x to the 6th stuff. I mean, we're going to have all kinds of issues with our x's, right? Let me just walk it through so you can see. So dx is du over minus 12x to the 11th. So if I put all this stuff in, I've got x to the 5th over the square root of u. Well, that was nice. Dx is du over minus 12x to the 11th. And even when I reduce those x's, I get minus 1/12 du over x to the 6th times the square root of u. And I don't want to try to bother solving this thing for x to the 6th. It's not a real quick and easy solve. So instead, what I'm going to do, and I saw that Devin put this in the chat, let's use u equals x to the 6th. Now, what's kind of driving this as a choice for you, honestly, is the x to the 5th, because if we differentiate this, du is 6x to the 5th dx, and you notice now that x to the 5th dx is all lumped in our u. So if we change this one using u equals x to the 6th, we're going to get 1/6 du over the square root of 1 minus u squared. Because x to the 12th is x to the 6th squared. So this one was really driven, this substitution was driven more by the remaining piece, because this is still a form we know how to do. Which inverse trig function is this going to lead to? What gives us a form 1 over the square root of 1 minus u squared? Yeah, good. Inverse sine. So this is going to be inverse sine of u. And it's just plain old u because this is 1. Right? This is the a squared minus u squared. So it's u over a or u over 1. All right, so we were able to anti-differentiate. Now, of course, we just have to put our x back in. So we're going to get 1/6 sine inverse of x to the 6th plus c. All right, so you're starting to see one of the potential issues we're going to have now with integration, specifically substitution, is it's not always going to be really clear which u to pick. Now we're starting to see all kinds of different forms. So I'm just telling you, you have to be okay. You have to be okay with picking the wrong u sometimes. It's going to happen. You're going to pick the wrong u. You're going to choose something, put it in, find out that it doesn't work. And if that's the case, all right, don't freak out. Don't just throw your paper away and say, screw it. Back up and think, okay, what are other possibilities for x, or for my u? What are other choices that would still give me a nice form? So with something like this, I'll just tell you, I mean, if you look at the inverse trig forms, you notice how the inverse trig forms have sum and difference of squares, right? Like with the inverse sine, it's literally a squared minus u squared. For the inverse secant, there's the u squared minus a squared. Yeah, there's some other stuff out front. And with the inverse trig, or inverse tangent, it's a squared plus u squared. Sum and difference of squares are actually really nice forms. So when you have something like this, you can recognize that this is a square by looking at the even power. So if you've got even powers, recognize that it's squares, and so therefore inverse trig might be something you want to use. All right, so any questions on this one before I jump to number 11? All right, so let's go see what number 11 has in store for us. All right, so we've got consider the integral. Negative integral of inverse cosine of 6y over the square root of 1 minus 36y squared dy. All right, so this one says this can be transformed into a basic integral by letting u equal what, which then makes du equal what, and then after substituting, you obtain the integral. All right, so this one's basically saying don't do the integral. We might go ahead and just do the integral, but let's at least get it set up. And we have to figure out the right u. All right, so I'm going to switch to the whiteboard again real quick. Let's clear all this stuff off. And let's think about this one. So we had the negative integral of inverse cosine 6y divided by the square root of 1 minus 36y squared dy. I probably should mention this. I didn't think about it back at the time. I know that like on this homework, I called it arc cosine, and I wrote cosine inverse. Those do mean the same thing. I'm not a huge fan of the arc because it's more writing. That's the only reason I just go straight to inverse. Why there are two, I don't really know. My guess is probably just to keep from getting confused with that -1 as meaning to a -1 power. But anyway, so arc cosine, cosine inverse, same. Okay, so let's just think about some different possibilities for our U substitution. One would be to let U equal 6y, right? That's a kind of an obvious choice because then this makes it cosine inverse of U, which is something that we could use and deal with. So that would be one choice. Another choice would maybe be, what if we let U equal 1 minus 36y squared? And you can see that one's kind of a nice choice because that makes this thing the square root of U, right? And notice also that this U equals 6y is kind of that same trick that we saw on that other problem where that makes this a difference of squares, 1 minus U squared. So that's another push for the 6y. But then a third choice would be, what if we just let U equal the cosine inverse of 6y? Now, what might make that worth doing is the fact that that's the biggest and ugliest part of this integral. So if we can turn that into a u, then we don't have to deal with nastiness. So I would say that these are probably our three best shots for our choice of u. Now, the one that I'm going to use, because I know it's going to work, is this guy. So let me share with you how I know that's going to be the one that we want to try. Basically what I do is I kind of run it through in my head and I think about what are the derivatives going to look like in terms of then using, incorporating that into the dy. So this one, the derivative is just 6. A constant multiple is going to leave all this other stuff as gross yuckness. I'm not going to be able to cancel anything. So I'm not going to pick that. That's a bad choice. 1 minus 36y squared, similar issue. Its derivative is minus 72y, which is going to leave all kinds of gnarly stuff. Inverse cosine, I know that its derivative is just the opposite of inverse sine. And inverse sine's form is 1 over the square root of a squared minus u squared. And I see here, I've got a 1 over square root of a squared minus u squared. I've got a really good chance of getting rid of all this garbage. So I'm going to use u equals cosine inverse of 6y. All right, so let's see what du looks like. All right, so the derivative of inverse cosine. Now, I didn't remind you about this one. I just showed you inverse sine. But I also reminded you that the difference between the derivative inverse sine and inverse cosine is just a sign, a plus or minus sign. So we're going to get minus 1 over square root of, right, so I'm going to get a squared, so 1 minus 6y squared. But then I need to multiply by a 6. Why? Why is this 6 in here?
Chain rule?
Yeah, it's exactly it. It's a chain rule. I'm differentiating the inner function, so there's a 6. So notice that almost all of this stuff is over here. I need a minus sign. There's my minus sign. I need a square root of 1 minus, well, if I square that, 36y squared. Okay, that's that. I don't have a 6. I mean, I've got a 6 in the inverse cosine, but I don't have a 6 just by itself. But I also have the dy. So I have almost everything I need. I'm just off by that 6, which means when I go and I do this integral and I change it into u's, I just need a 1/6. So I'm going to get 1/6 u du. Because the inverse cosine, that was u. All the rest of the stuff is in there is the du with the exception of the 6. So if I divide out the 6, maybe this will show it to you a little bit better. So all the stuff I circled there in green is the right-hand side of this. So I just replaced it with the left-hand side, the du over 6. So hopefully this at least kind of shows you my thought process when I'm trying to decide what U substitution to do. But like I said, you got to be okay with picking the wrong one and then backtracking and trying something new, because it's gonna happen. All right. This is definitely one of those places where, you know how nowadays we sort of have this expectation of instantaneous gratification, right? Oh, who was the actor that was in, in The Good, Bad, and the Ugly? You just type into Google and it tells you, right? Or you say, hey, Alexa, right? So we're really used to getting stuff right away, immediately. Well, in calculus, it's going to be the case where that doesn't happen. So even though we're kind of used to that in our everyday life, we got to realize that. Yeah, so Clint Eastwood was the main star of it. Lee Van Cleef was the bad, right? Clint Eastwood was the good, and then Eli Wallach was the ugly. One of my favorite movies. Anyway. All right, so this is what it looks like. So in terms of what you're putting into the boxes, we're going to let u be inverse cosine of 6y. Du is going to be all this garbage. Ugh. But then the integral is just 1/6 u. So I actually do want to finish this one off. Let's go ahead and get it. So the 1/6 is a constant multiple. U gives us u squared over 2. So when we put back in our u, we're going to get 1/12 cosine inverse of 6y squared plus c. So this is the antiderivative of this ugly, gnarly looking thing. So this is also kind of the power we now have. I mean, we can have really ugly looking things and still be able to get their antiderivatives. So some more advice I have for you with these is treat them like a puzzle, like a game, right? This is the game. It's the puzzle. I'm giving you a function and you're trying to figure out the antiderivative. So think of it as a game or a puzzle, and you want to win, right? You don't want me to win. You want to win. So practice just like any other game. Practice the skills, but also practice the strategy, right? And that's what this is, the deciding which of the U's. that's the strategy of anti-differentiation. All right, so is that better for number 11? Any other questions? All right, so hearing none and seeing none. Oh, we got a new student in the class. These calc students get younger and younger all the time. For those of you who can't see, Blake's got his kid in his lap. So anyway, all right, so let's go ahead then. I'm going to switch up to the whiteboard, and I want to show you how we deal with completing of the square and what that does in terms of leading us to inverse trig functions. And then that will make the, whatever number that was, 7 or whatever, you'll see a little bit more how you can approach that. So I'm going to go ahead and switch screens. I'll be right back with you. All right. So the inverse trig functions. I know you probably don't love them, probably don't remember a lot about them. Get to know them. Get to know them. The better you know their derivatives specifically, the easier this stuff's going to be. But I do want to show you completing the square and how that's useful. So first, before we use it for anti-differentiation, let's just talk about how we complete the square and what that means. So back in the day, you first ran into this when you learned the quadratic formula, right? When you're dealing with solving quadratics, you learn completing the square as a form to do it, as a way to do it, method to do it. But then you promptly forgot completing the square because you got the quadratic formula. So why complete the square when you can just use the quadratic formula? Okay, but hopefully at that point, someone said, don't forget about completing the square because you're going to need it again later. Now, you guys should have also run back into completing the square when you're dealing with like conic sections. Remember circles, ellipses, hyperbolas, stuff like that. Completing the square is a process that we use there. So you ran into it again there. If it was a pre-calc class, hopefully your teacher again said, and don't forget about completing the square because you're going to need to use it again later. Because here's another place where we're going to. So just to help you remember how to do that, let's walk through the process of completing the square. All right. So for example, let's say we had x squared plus 9x minus 7. And we want to complete the square. Now, completing the square means we want to write it as a binomial being squared. You know what? I don't want 9. I don't want to be that mean yet. It's too early. Let's go with an 8. We'll make it x squared plus 8x minus 7. Okay, so here was the process with completing the square. All right, so what you do, well, first, you look to see the coefficient on x squared. You have to make sure it's a 1. Okay, so we've got 1x squared. As soon as you have that, you can jump into the completing the square process. So what we're going to do is we're going to take the b, the thing that's on x, and we're going to divide that by 2. So we're going to take 8 divided by 2, which is 4. Divided by 2 is 4. All right, then we're going to take that number that we just got, 4, and we're going to square it, which gives us 16. Okay, so the process is always divide by 2 and then square. Divide by 2, square. Divide by 2, square. Just always divide by 2 and then square. Now, that number right there, that's 16, we're going to add that in. But if I just add 16, I've changed this. So I'm going to subtract 16 at the same time. All right, so I've got my plus 16 minus 16. This is one of the oldest tricks in the math book. We just added 0. Right? We added 0. We didn't change anything, and yet we turned it into a completely different form. All right, well, here's what I'm going to do. I'm going to rearrange some things here. I'm going to bring that plus 16 up with the x's. So I've got x squared plus 8x plus 16. And then I'll leave the other two pieces just so you can see them. So I really just swapped those two. All right, but now here's the deal. If you look at that first set of 3, that's a perfect square trinomial. It does factor, and it factors as x plus 4 times x plus 4. So this is x plus 4 squared, right? The bit in the parentheses. And then the minus 7 minus 16, that's minus 23. And what we just did was we just completed the square. So completing the square is taking it and writing it as a perfect square. Right? So it's x plus 4 squared. And then we got the remaining bits. Okay, so this is the general process. This is what you do. You take that coefficient on the linear term, on the x term, divide it by 2, square it. All right, but you may remember that I said, but you have to make sure you have a single x squared. If you don't have one x squared, you have to adjust this a little bit. All right, so let me show you how we do that. So here's another example. But let's say we've got 2x squared plus 3x minus 1. Okay, so we can't dive straight into the divide by 2 and square because of this 2. So here's what we have to do. We actually have to factor out the 2. So I'm going to divide everything by 2. Now, for those other numbers, the 3x and the minus 1, dividing out the 2 leaves us fractions. And that's totally okay. And you should expect that to happen a lot when you complete the square. It's very rare that you don't end up with fractions. Very rare. Okay, so we have some fractions now, but at this point, we go to what we know we need to do. We're going to take that coefficient that's on the x, so in this case it's 3/2, and we're going to do the same thing that we did before. We're going to take that 3/2 and divide it by 2, which gives us 3/4. And then we're going to get that 3/4 and square it, which gives us 9/16. So again, divide by 2 and square. The fact that they're fractions, so what? So what? The process is divide by 2 and square. So now that we have that 9/16, we need to add that in and subtract it out at the same time. Okay, so when we've done this, where we've factored out something, you need to make sure that add and subtract happens inside that factoring. So I'm going to put my plus 9/16 and minus 9/16 both inside of this factoring. And as long as they're both inside, you're still adding 0. If they were both outside, that's fine. If you had like a 9/16 in the parentheses and then the minus 9/16 outside, now you didn't add 0. So you need to make sure you keep them together. My recommendation, just keep them inside the parentheses. Okay, so now we're going to look at those 3 pieces. The x squared plus 3/2 x plus 9/16. That is a perfect square. And what it's going to be is x plus 3/4 squared. I still have my minus 9/16 minus 1/2. And if I put those together, that's minus 17/16. Getting common denominator and whatnot. All right, but again, we just completed the square. We wrote it as a perfect squared term. Before I leave this one, I just want to either remind you of or tell you the shortcut for figuring out what's in the parentheses here. So you might have seen this because the pattern is definitely there. But what you end up with, what you add or subtract from x is what remains after you divide by 2. If you come back to the very beginning here when we did the divide by 2 and square business, if you look at what we got when we divided by 2, so in this case that was 3/4, that's the same as what's being added here. And you'll see the same thing happen with this first one. After we divided by 2, we got 4. And notice that it was x plus 4 squared. So that's just a little bit of shortcut. Use it. It's especially useful when you've got gnarly fractions. Anyway, so this is completing the square. So now, what does this have to do with doing integrals? Well, remember how the inverse trig functions, all of their integrals have to deal with squares, right? Where you got a squared plus u squared, or a squared minus u squared, or u squared minus a squared. If you can take a polynomial and complete the square, sometimes it turns into a squared plus u squared, or a squared minus u squared, and then we can do our anti-differentiation. So let me show you a couple of easier examples, and then I'll talk more about that homework problem that you guys asked about, number 7, I think it was. So how about this guy? Let's look at the integral dx over x squared minus 4x plus 7. All right, so looking at this one probably doesn't do much for you because it doesn't look like any of the forms that we've seen. You could think about trying to do a U substitution for the bottom, but if U is equal to all of this stuff, the du is going to be a 2x minus 4. We don't have any of that. Yeah. Okay, so instead, let's complete the square. Let's just see what happens when we complete the square on this. So we need to look at the b term, the term on the x, which is -4. So we're going to take -4, and we're going to divide it by 2. This is -2. And then that -2, I'm going to square it, which gives me 4. All right, so in this integral, I'm going to both add and subtract 4. So I'm going to put plus 4 minus 4. And we still have the 7. So again, I didn't actually add in anything. I added in 0. All right, but that first set is now a perfect square, right? Those first 3, if I look at these guys right there, that's going to be x minus 2 squared. That's how it factors, or come back and look at what we got after we divided by 2 was -2. And then, of course, 7 minus 4, that's 3. So let me just rewrite this real quick. I'm going to switch the order because I think it'll be a little bit easier to see. So we've got dx over 3 plus x minus 2 squared. All right, so up to this point, only algebra. We haven't even touched calculus. This was only algebra. Start getting it into a form that we can maybe use. All right, so this is now starting to look like inverse trig. Which inverse trig form is a squared plus u squared on the bottom? All right, thanks, Rigney. It's inverse tangent. So this one's definitely going to be an inverse tangent form. But I need to have like a u here. So let's do a u substitution. So we're going to let u equal x minus 2. So du is equal to just plain old dx. So it's going to be a nice easy swap. So this integral then becomes the integral of du over 3 plus u squared. All right, so that's going to give me an inverse tangent. But in that inverse tangent, I need u over a. And the a is the square root of this guy right here. So it's going to be u over root 3. And then the other thing we saw with the inverse tangent is we need a 1 over a out front. So this is going to be 1 over root 3 times inverse tangent of u over root 3 plus c. But as always, we want to replace that u. So what we end up getting is 1 over root 3 inverse tangent of x minus 2 over root 3 plus c. We'll go ahead and put a box around that so we know we're done. But there's the antiderivative of dx over x squared minus 4x plus 7. All right, so again, this was all algebra that led to the difficulty here. The integration itself, I mean, that was this step. Here was the calculus, by the way. It's this little bit in purple. One step of calculus. And it was basically just remember what the form is and plug stuff in, right? The rest of it is all algebra. But by completing the square, we got it to a form where we could do it. And to a mathematician, and I know a lot of you aren't mathematicians, but to a mathematician, it's all about, can it be done? We don't care about the fact that there's going to be a lot of work to get there. It's, can we do it? The answer is yes. We can do this, so it's a win. We just won the game. We just beat the puzzle. We had to go back into our brains and find all these great tools to use, but we were able to do it. All right, so there's where completing the square can actually help. So here's an example that was not terrible. I mean, yeah, it ended up that we had to have a square root as our a, but they can definitely get worse. So let me show you another one that's a little bit more complicated, but before I do that, I just want to give you guys a chance to ask any other questions you've got on this, because I know you got them. There are always questions when we do completing a square. All right, I'm going to trust you that you don't have questions. So let me show you another one, just for a little bit more practice. All right, so how about this? Let's make it a definite integral. So we'll put some bounds on here. And our definite integral here, we're going to go from 3/2 to 9/4. And then what we're going to be integrating is 1 over the square root of 3x minus x squared dx. All right. Okay, so again, look at this form and think about what are the different things we know what to do. So a good thought would be, what if I let 3x minus x squared just equal u? So now we've got just the square root of u. But you can see that that's going to run into problems real fast. When you get your du, it's going to be 3 minus 2x, which is not part of this, and trying to replace that x is going to get tough. So we probably don't want to do a u sub. Okay, so then the other thing that you should think is, ooh, I've got a square root of stuff with a square in it. Maybe I can turn it into inverse trig. Maybe, hopefully. But in order to do that, I have to complete the square. So let's complete the square. I'm going to go ahead and complete the square kind of on the side. We'll run through the completing the square process and then put it back in. So let's just think about what this would look like if we're going to do completing the square on minus x squared plus 3x. So I just swap the order so that we're leading with the x squared. Okay, so let's complete the square on it. So first things first, notice that the x squared is not 1x squared, it's minus 1x squared. So we have to factor that out first. So if I pull out a minus sign, it just changes the signs on those two pieces. All right, so now we get to complete the square. So my coefficient on x is minus 3. And I take minus 3 and divide it by 2, which gives me minus 3 halves. And then I'm going to take that minus 3 halves, and I'm going to square it, which gives me 9/4. All right, so there's my completing the square. So let's add and subtract that 9/4. But again, we need to make sure that we do that together in the parentheses. So we're going to put plus 9/4 and minus 9/4. So I really added nothing. All right, so now if you look at these first three pieces in here, that is a perfect square. So that's going to be minus. And now we've got x minus 3 halves squared minus 9/4. And the last thing I'm going to do is actually distribute that minus sign through. So I get 9/4 minus x minus 3 halves squared. All right, so there's the completing of the square on what's in the parentheses. So all of that algebra, all that did was it got it so that we can rewrite this integral as 1 over the square root of 9/4 minus x minus 3 halves squared. Whew. All right. Now, was that helpful? Hopefully, right? Otherwise, there's no reason to do it. But this is definitely better because this is starting to look like one of the inverse trig forms. Right? This is starting to look like a squared minus u squared in a square root. So which of the inverse trig forms was that? All right, cool. A couple of you, Adam, Rigney. Oh, all kinds. Inverse sine, for sure, is what we want. This one's going to be inverse sine because that's the one that's the 1 over the square root of a squared minus u squared. So that means we do need to do a u substitution, but we know how to do that. We'll let u equal x minus 3 halves. So du is equal to dx. So that changes this integral into a 1 over the square roots of 9/4 minus u squared. Cool, exactly what we wanted. A squared minus u squared. The dx is a du. And while I'm here, I'm going to change my bounds. Okay, I'm going to take those 3/2 and 9/4, and I'm going to plug those into my u, right? And as my x, actually, let me plug in as the x. We got our new u values. So when x is 3/2, u is 0. And when x is 9/4, 9/4 minus 3/2, that ends up giving us 3/4. Because 3/2 is 6/4. You take it away. All right, but now we're ready to go. Now we're ready to get our inverse sine. Okay, so when we anti-differentiate this, we're going to get inverse sine of u over a. So it's going to be u over 3/2. And that's it. That's our antiderivative for the inverse sine. It's just inverse sine of u over a. So now we need to evaluate this at 0 and 3/4. So let's put those bounds in. So 3/4 divided by 3/2. You flip and multiply and all that, you get 1/2. This is the inverse sine of 1/2 minus the inverse sine of 0, because 0 divided by anything is 0. All right. These we can actually evaluate. These are nice numbers. So if you remember your trig, which, let's be honest, most people don't, there is an angle whose sine is 1/2. Maybe somebody does remember. Anybody remember the angle whose sine is 1/2? Awesome, thanks, Adam. It's pi over 6. All right, so inverse sine of 1/2 is going to be pi over 6. How about the inverse sine of 0? What angle gives you a sine of 0? Cool. Also 0. Thanks, Adam. So you have pi over 6 minus 0, which is pi over 6. So again, let's go ahead and box that just so we got everything all nicely, neatly figured out. But there you go. The value of that integral is actually pi over 6. If you were to look at the graph of this function and look at the area underneath it between 3/2 and 9/4, it's pi over 6. All right, but there's no way we would have gotten there without completing the square. All right, so go back and look at that one from the homework, right? You guys can go back and look at it or review the video. I don't remember exactly what it was, but we ended up getting in the denominator a square root of, it was like x squared plus 4x or something. I don't even remember exactly what it was. But if you go back and you look at that, you can complete the square. By completing the square, you can change the form. And hopefully by the process of completing the square, you get into a form that is now easier to integrate. Okay, so just be aware that that pops up all the time. So I'm going to go back and look at that homework problem and try that later if you're still having trouble with it. And see how completing the square goes. Of course, on Wednesday, if we're still having issues, we can look at it again. I just don't remember what it is. All right, so inverse trig functions are going to show up. Get to know them, review them, remind yourself what their derivatives look like, because the better you know the derivatives, the better you can anti-differentiate. Okay, so we've got about a half hour left, and I want to start showing you another application. So Bruno, I extended that homework to Wednesday. I mentioned that earlier, but I'll mention it again. 1.7, its due date is now Wednesday night at midnight. So you have a couple more days to work on it. Gives us another chance to talk about this kind of stuff as well. All right, so I want to start showing you some more applications of integrals beyond just the area underneath a curve, or the signed area, actually, to be more precise. But today, I'm going to show you something that's not a huge difference. It's not something very different. We're going to be looking at what about like the area between two curves. All right, so if you look at what we've done so far with the integral in terms of the application to area, you can tackle shapes that look like this. Right? You want to find that area. If you know this thing is f of x, and these are the places a and b, the area is going to equal the integral from a to b of f of x dx. So when you have a shape like that, you know what to do. Not that big of a deal. But there are all kinds of other shapes out there that don't kind of conform to this. Like, what if we just change this ever so slightly? So it looks like this, where now we still have a to b, but both the top and the bottom of this shape are defined by functions. Okay, so I'll call this one f and this one g. So what I'd really like to be able to do is extend it from what we were doing, which was just looking between a curve and the x-axis. What if instead I want to look at the area between two curves? Okay, so that's what we're going to do today. We're going to talk about how to get the area between two curves. Well, it's actually really easy. Because all you got to do is think about it the same way that we did before. Think about what we did. We took this region and we split it up into a bunch of rectangles, right? So we partitioned this, and then we used those rectangles to approximate the area of this thing. And then we did basically a limit. We made an infinite number of them and added them all up, right? So think about how we built this. Those rectangles had a width, call it dx. How did we get the height of the rectangle? Yeah, we just plugged in an x into the function, right? And so to get the area of a rectangle, it was f of xi times delta xi. So this was the height, and this is the width. And then to get the actual value, we just took the limit as n goes to infinity of the sum of these things, right? And that ended up being the integral. So we broke it down into rectangles and then added them up. Well, let's come down to this picture. I want to get rectangles that approximate this area, and I'm going to do kind of the same thing. I'm going to divide this region up into partitions. And then in each of those partitions, I want a rectangle that approximates this region. So I'm just putting a bunch on here just so that we actually have them. All right, so here are, in this case, the 6 rectangles that come from this partition. All right, now notice first of all that the difference with the rectangles that I used to approximate this. One big difference is they don't go all the way down to the x-axis. Because if I drop those rectangles all the way down, I'm going to get way more area than I want. Right? Okay, well, think about how I get that height. I want the height of this, I need to know where the top is versus the bottom. Well, the top is determined by f of x. The bottom is determined by g of x. And if I want to get this height, I just have to subtract those two numbers. So in this picture, what we got going on is that the height is going to be f of xi minus g of xi. That's going to give me the height of any one of these little rectangles that we're approximating. Well, the widths are still delta xi. So when I put this all together, I'm going to get the limit as n goes to infinity of the sum from 1 to n of f of xi minus g of xi times delta xi. And with just a slight little amount of algebra, basically distribute these and then split it up because I've got two things that are being subtracted. We saw that sums of differences, you can do each one separately and subtract. Limits, you can do each one differently, individually, and subtract. And so what this ends up being, and I'm sure this is going to come as no surprise to anybody, is the integral. I'll write it down here. So the area is the integral from a to b of f of x minus g of x dx. So it's almost like nothing is different here. It's just when we get our heights of our rectangles, they're found by doing the difference in the two functions. That's all there is to this. It's really not that complicated. So if you've got a shape and you know the function that defines its top and the function that defines its bottom, just subtract those two, take the top minus the bottom, and integrate that over your bounds. And that's going to give you the area between the curves. All right, so go ahead and box this guy, this area between curves. Because this is the one we're going to use. We're going to use this a lot. Let's take the pen off. All right, but let me just show you some examples because it's really not that difficult. It's really straightforward. It's just a matter of knowing your top and your bottom, and maybe we have to do a little bit of work to figure out the bounds. But we just need to know what's on top, what's on the bottom, and we subtract it. All right, so let me show you an example. So let's say we want to find the area between y equals e to the x and y equals x squared when the x's are between 0 and 1. And we'll even start by drawing the picture. Let's draw a picture of this thing because we know what these functions look like. Let's draw a picture of this region just so we can see what we're actually calculating. All right, so here's some axes. We've got y equals x squared and y equals e to the x. So y equals x squared does this. Not very symmetric, but there's our y equals x squared. And then y equals e to the x. That does something like this. And we're going to be between 0 and 1. So here's x equals 0. Here's x equal 1. So we're looking at the area of that shape right there. Okay, so that black hatched in region, that's what we're looking at. All right, well, it's actually this easy. All you got to do, set up our integral. We're going from 0 to 1, and we take top minus bottom. So the top function is e to the x. The bottom function is x squared. And there you go. That's the integral that's going to give us this area. So hopefully you can see that it's not like this is that much crazier than what we did before. The setup is barely anymore. And in fact, now that we go and we want to anti-differentiate, okay, it just means we have more things that we're anti-differentiating. It doesn't really affect much. So this is going to be then e to the x minus x cubed over 3, evaluated at 0 and 1. When I plug in 1, I get e minus 1/3. When I plug in 0, I get 1 minus 0. Don't forget e to the 0 is equal to 1. And so the area of that region, of that shape, is e minus 4/3. Put a box around it. We're done. So it's pretty easy. But think about what it allows us to do now. We can actually calculate so much more when it comes to areas, so many more kinds of shapes. And all it was a subtraction. Easy. All right. So you just got to know what's on top, what's on the bottom, subtract them, and then go from A to B. All right, so let me show you another one. Let's try this guy. Let's find the area between y equals x squared minus 4 and y equals minus 2x. Now you notice I didn't give you any bounds on the x's. And that's because these two curves create an enclosed region. So we're gonna have to figure out what the bounds are, but let's look at the picture first. All right, so x squared minus 4, you all know what that looks like. It's a parabola. And its vertex is down at minus 4. So it's a good old happy parabola that shifted down. So it looks like that. And then y equals minus 2x is a line. It's a line with slope minus 2 that goes through the origin. And so it looks, pretend that goes through the origin. We'll just make the dot really big so it goes through the origin. There's our y equals minus 2x. And so you can see that this definitely forms an enclosed region. And it's that little thing right there. So we're trying to find the area of this thing right here. All right, well, let's get it set up. So we're going to have an integral of, we'll worry about the bounds later, but let's start with the top minus bottom. So the top of this thing, the green one, is the line. So we're going to have minus 2x. And then we're going to subtract the parabola, which is x squared minus 4. Okay, so we're going to have minus 2x minus x squared minus 4 dx. And now we got to get the bounds. We have to figure out where do those intersect. So do you remember how to do that? Do you remember how to actually figure out where two graphs intersect? Okay, yeah, so you set them equal. Thanks, Adam and Erez, throwing that in the chat. What you do is you take these two functions and you set them equal to each other and solve. So we're going to take x squared minus 4 and set it equal to minus 2x. So that's x squared plus 2x minus 4 equals 0. Right? And if we wanted to figure out where that equals 0, we're going to have to use a quadratic formula. We're going to have to complete the square, something like that. I'm going to jump to the quadratic formula. So x is equal to negative 2 plus or minus the square root of b squared minus 4ac, which is 20, divided by 2a. So this is minus 1 plus or minus root 5. Okay, so these are not nice numbers, right? They're not whole numbers, they're not even fractions. They're irrational, but that doesn't change anything. We can still use those as bounds. So the bounds are going to be minus 1 minus root 5 on the bottom. But nice one, minus root 5. And the upper bound is going to be minus 1 plus root 5. So we're going to go ahead and anti-differentiate, plug in those bounds, do the subtraction, and we'll now have that area. Okay, so if you get bounds like this, don't freak out. It's okay. We really tend to look down on numbers like these, right? We don't like them, but they're no different. They don't behave any differently than numbers like 4. You just know 4 a little bit better. These are fine. Plug them in. You're still going to get whatever the values happen to be. All right, so I'm going to leave this one here for the sake of time because we know what to do. We know to anti-differentiate, plug these things in, and get whatever weird root answers we get. All right? But sometimes we got to do this. Sometimes we have to figure out where do these come together, where are the intersections, so that we can actually find our bound. All right, but again, it comes down to top minus bottom, top minus bottom, top minus bottom. It's always top minus bottom. All right, well, let me show you another kind of twist that we can get, or something that we have to watch out for. And we're going to go back to our good friends sine and cosine here. All right, so again, just like before, I want to find the area between y equals sine of x and y equals cosine of x. And I'm going to give you a region again. We're going to go from 0 to 2 pi over 3. So if you think about what we've done so far, we have to know our bounds from where to where. Okay, well, we're given a region, so we don't have to worry about that here. Right? It's not like we did on this other one where we had to solve. And we need to know top minus bottom. We need to know which one's on top and which one's on the bottom. So really, that's what we have to do here, is figure out which of those is on top and which is on the bottom. All right, so quiz for class. Which one's on top and which one's on the bottom? So let's go with which is on top, cosine or sine? All right, so Bruno says sine. Uh-oh, Mariola says cosine. Oh, and then Stephanie says both. And then Erez is actually, they weave, right? We know sine and cosine cross each other. And what ends up happening in this region from 0 to 2 pi over 3 is that for a while, cosine is top, but then it switches to sine being on top. Here are their graphs. So here's cosine. Right, there's the graph of cosine. I'm only going from 0 out because we don't care about because that's our region. There's cosine, and then here's sine. Ugh, I did not draw that very well. We're going to go with it. But I liked errors when errors wrote they weave. That's a great descriptor here. Yeah, they weave together. Sometimes cosine is on top, right? The blue is on top sometimes. Sine is on top other times. And if we look at the region that we're dealing with, 0 to 2 pi over 3, well, obviously 0 is right here. 2 pi over 3, I know you can't really tell very well because I did not draw these all that well, but 2 pi over 3 is here. And so somewhere between 0 and 2 pi over 3, these things swap. So if we're trying to find the area between these things, we're looking for what I've just kind of hatched in purple. It almost looks like a pair of angel wings or something like that. Non-symmetrical angel wings. That would be me as an angel. I probably have like all kinds of weird stuff going on. Okay, so we have to calculate these. So when it comes to top minus bottom, it depends where we are. So in this case, what we need to do, we need to set up two integrals. We need to do one integral for when cosine's on top, and the other integral for when sine's on top. So we're going to break this into two. Okay, get this area is equal to, the first one is going to be from 0 to somewhere. We'll worry about this somewhere in a second. But for the first integral, it's going to be cosine minus sine. And then we're going to add to it another integral that goes from that wherever spot to 2 pi over 3 of sine minus cosine. So in a situation like this, where your curves, their role as top or bottom changes, and this can happen a lot, right? I mean, you can think of lots of situations where this could occur. When this happens, you have to break it into the different pieces, one on top where we've got top minus bottom for the different situation. All right, so we got to still figure out that question mark. Where is that point? So how are we going to figure that out? Actually, some of you just may know. But what are we looking for there? Well, I'll give you a hint. Yeah, there you go. Thanks, Rigney. It's the same thing we did with the other one where we tried to find the area between that parabola and the line. We need to set them equal to each other. So this place right here is going to be where sine equals cosine. Because it's an intersection point. All right, so we need to solve sine of x equals cosine of x. So some of you may know that. Anybody know the angle in here where sine and cosine are equal? It's a nice angle. It's actually pi over 4. Sine and cosine are both root 2 over 2. So this is going to be from 0 to pi over 4, and then pi over 4 to 2 pi over 3. Okay, if you actually needed to solve this, you'd square both sides. Sine squared equals cosine squared. Then you would replace either the sine squared or the cosine squared using the Pythagorean identity. Solve that remaining equation. You're going to get, if you solve it for sine, you get sine equals plus or minus root 2 over 2. Cosine equals plus or minus root 2 over 2. and then you'd have to use your inverse trig. Just smile and nod. Yeah, okay. All right, so it ends up then, in this case, we're going to need two integrals. And there you go. So again, I'm not going to bother finishing this one because you know what to do. Integral of cosine is sine. Integral of minus sine is cosine. And vice versa, plug in your bounds, get your numbers, and you're done. And you'll have that area. Okay, but the moral of the story with this one is when they swap, top versus bottom, we have to account for that. And we have to basically manually decide where to switch those two. All right, so how are we feeling about area between curves? Is it really as easy as I contend that is? Okay, I like that. So Rigny's put in the chat box that it's moderately solid. All right, I like that. That's yeah, for the most part, it feels pretty good, right? And Adam just concurred with you, so that's nice. And I saw a couple of thumbs up in the window. So it really isn't a big stretch from what we were doing before. It's just it's giving us now a bottom. All right, there is one more thing though, one more little tweak that we have to worry about with these things, area between curves, but we don't really have time to go into it today. So I'm going to save that for Wednesday. The hook to bring you back, right? So here's kind of what's going to happen on Wednesday. We'll go over the quiz. I'll have it all completely graded. It's mostly graded. There are only a couple of you I still haven't finished. So we'll go over the quiz on Wednesday. We'll address any other homework questions as always. Then I just want to show you one more kind of quirky thing with area between curves. It's basically I want to show you something that will help you out. It's just a change of perspective kind of thing. And then we'll start talking about a completely different application, although it's not completely different, but it feels different. We're going to start talking about volumes, how you can use integrals to help you actually calculate volumes. So that's the plan for Wednesday. But other than that, I'm going to go ahead and pause or stop our recording, unless there are any last minute questions for on the record. All righty.